So let's continue with that. Where did we stop? We talked about how computers are getting faster, fancy artificial intelligence, how it can learn to play a game against itself, and that makes it super good because it can play more games than any human ever could. Fun stuff. Yeah, let's talk a little bit more about artificial intelligence. Probably one that's very near and dear to our hearts. Either we love it or we hate it, or something in between. Self-driving cars, right? Essentially, a self-driving car, it needs to have some sensors, some sonar, some cameras. It needs to draw boxes around interesting things. It's essentially that blink detection all over again. Where was that? This blink detection, trying to discover when somebody's eyes were open or closed. That is essentially what self-driving cars are doing, but they're doing it on a very much larger scale, right? So they're drawing some more boxes than just around faces and eyes, right? They need to notice the other cars. They need to notice if there are any pedestrians in the way. They need to notice the traffic lights. They need to pick those out, especially in a weird-looking scene where it might be hard to notice that there are traffic lights. It needs to be able to find all of them, right, where those are. And it needs to know which side of the road it can drive on. It's like green side's for me, red side's not for me. It needs to find those dividing lines, which it's a non-trivial problem. As a human, we're just used to it, but try and teach a computer all this stuff, it's pretty hard. Okay, so that's the kind of thing that a self-driving car needs to determine rapidly as it's trying to move around, as it's sitting at a stoplight, as it's pressing on the accelerator for you, right? It needs to figure out where all those pieces are, all the other cars, the stoplights, pedestrians, and then once it's drawn those boxes and figured out what the things are, it needs to process that information, right? If the light's green and the pedestrians aren't in the way anymore, now we should go. Press on the accelerator, turn the steering wheel. It looks like we need to go over to the right a little bit to go straight. Crazy, right? So that is what self-driving cars are all about. And now that you know a little bit more about artificial intelligence, it's not too magical, I would say. It's a hard problem, but it kind of makes enough sense. It's just you train it, right? You give it you drive it a lot. You have it try to predict things. You give it what it should do, and it should learn from that. And just as an aside, I've been reading that it might not make sense to ever own a car in the future, because if they're all self-driving, you could just click on an app and a self-driving car would appear at your doorstep, take you where you need to go, and then go off and take somebody else somewhere else. So that could be a future that would be potentially exciting. That's a future we could be living in one day if they ever get self-driving cars fully self-driving. Any questions, comments about that? And so this is a hard problem, right? It's a hard problem, and people have tried to break this, right? People have tried to hack it, and that's one of the major issues, right? There's that video of a Tesla accidentally running into a dummy child or something, and that caused a lot of controversy. That kind of stuff needs to be worked out before self-driving cars become a thing. So some people, they put a little strip of tape on a speed limit 35 sign. They made the little hooky part of the 3 stick out more, and that made two Teslas think that the speed limit was 85 rather than 35. And the car just accelerated, started going that speed. It's that's what I think the speed limit is. So that kind of stuff are problems. Those definitely need to be solved. Maybe you can hook a beacon chip on every speed limit sign or something, and have it always with a radio signal tell the Tesla how fast it really should be going, just in case somebody messed with the sign, or there's dirt all over the numbers, something like that. But yeah, this is a huge problem that I hope they've fixed by now, right? Maybe we've heard about that. But that is self-driving cars in a nutshell. Exciting times. Any questions about that? I just have a few more examples, then we're going to switch gears to a new set of slides today. So yeah, my next example, if we're good to keep going, is social media. Bad stuff, of course, happens on social media. We've talked about that. There's plenty of fallacies that I'm sure you've all have started finding, right? you can say bad things on social media, and a lot of the time it goes undetected. Bad things as in stuff that should not be there, like hate speech, right? Let's take Twitter as an example. Like, no human, you can employ 1 million moderators on Twitter, but there's like 1 billion tweets a second, probably. Something like that. You can't see millions of tweets a second. You can't employ enough humans to moderate all of Twitter. So you have to use programs to look for bad things like hate speech. Unfortunately, those programs aren't going to catch everything, right? But the solution to the problem, the reason that Twitter catches a lot of the hate speech that's on Twitter, that could have been tweeted and gets them off before your eyes can see them, good for us, what they do is they use the state-of-the-art technology in an area of artificial intelligence called natural language processing. Okay? That's what they do. They use natural language processing to look at the text, break it down like subject, object, verb, all that stuff, and they analyze the words in the tweet, for example. One type of natural language processing is sentiment analysis. And that takes the tweet and it discovers like, hey, based on those words, it sounds like the person is making fun of something or that it's a joke. Based on these words, it sounds like this person is scared. It sounds like this person is sad. It sounds like this person is very angry. And based on that, like, you can give some percentage to the sentiment that it finds, or a combination of sentiments that are fine. In that case, it can like discover the tone of the writing, and maybe if the tone is in the wrong direction, it can give that particular tweet to the human, right, to go and look over and make sure it's okay, and maybe delete if it's a bad thing and shouldn't be on Twitter. Okay, that's essentially what's going on. That's what computers are doing, using natural language processing to analyze the text of a tweet, of a comment, all that kind of stuff, to make it so that most of the bad things are not ever appearing on your Twitter feed. Okay? That's the idea. All right, next idea. So maybe you've heard this before. There's a game called the Turing test, and this, I couldn't teach you artificial intelligence without mentioning this. The game is called the Turing test. Maybe you've heard of it before. It's named after Alan Turing, of course, very famous. And here's the game. This is supposed to be like the goal of artificial intelligence is to pass the Turing test one day, right? So here's the game. Let's pretend that you are taking part in a research experiment that's going to perform this Turing test. So a researcher is going to take you into a room, close the door, and all that you have inside of that computer is a computer, right? Here's you. You've walked into the room. You have a computer sitting in front of you. They give you a laptop, and on that laptop they have like some chat room open, like they have Discord. They give you a Discord program open, and you can start chatting. Okay? And that's the experiment. So you know that there is one human in the chat room. Like here are the two people that are connected to Discord right now, along with you. There is one human in the chat room, and then there's also a computer pretending to be a human. So these are the two people you're talking to. One is real, one is fake. One is a computer generating the text to respond to you with. And you can ask those two members of the chat room questions, and they'll reply in text form. And at the end of the experiment, you have to like write down your best guess of who you thought the computer was, because you knew ahead of time one of those people was a computer. Which of those chat participants do you think the computer was? That's the Turing test. And if you are unable to tell if the results are, with enough people, about 50%, it's guessing on average, if you end up with those kind of results where the human is not reliably able to tell the difference between the human and the computer, that means that the computer passed the Turing test. Okay? So that's like the goal of artificial intelligence, is to pass this Turing test. To make a computer that can respond to arbitrary text in a way that makes it convincing that they're a human, that tricks you into thinking that they're real. Okay? And computers are actually pretty good at this these days. Depending on like how long the test is, the type of questions that you ask, computers can really do quite good. They can fool a lot of people these days. And so, like, I'm sure you've seen like chat bots on like a Discord that can respond to potentially any arbitrary text that you send. Or if you go to like a website, they have that little page that pops up that gives you like a picture of a fake human, and then you start typing and talk to that human, but they're not real. So that kind of thing. And they can usually figure out what you're asking for, right? Just with their textual analysis. And so that's an example of computers talking to you, right? Maybe you've experienced this. But that's the Turing test. That's like the holy grail of artificial intelligence. We would like to make a computer so smart that it can essentially function as a human. Trick a human. Any questions about that? That's a fun idea. You haven't heard of that before. So I have a fun experiment for us to try on 2 slides from now, but before we get there, I need to motivate the topic. So here is an article on the right. Let me zoom in here. Please read it. I'll give you like a minute or so to just skim through it. But here are some words. Please read most of the words. And then I will tell you something about this article. Try and guess what I'm about to tell you. I think that was enough time to at least skim it over. This article is not real. It was completely made up. It was written by a computer entirely. None of that was true. Isn't that awesome? That's pretty cool. It was just given a short prompt. It was like given the title or something. Like they gave this program the title of this fake article, and then it just rolled with it. It started writing that text, and it sounded convincing, right? It sounded like a real news article. So, yeah, that is the state of the art these days. It's called GPT-3. It's a neural network, of course. That's the most popular way to do machine learning these days. So it's a virtual brain, and it's doing text generation, okay? There are 175 billion fake neurons, virtual neurons, controlling this virtual brain, and it just decides, based on what it's written before, the next word to write, the next word to write, the next word to write. So you just give it some text, and it starts writing. That's so cool. So English teachers hate this, I'm sure. One day you're going to be able to just enter in the prompt for your essay, maybe even for this class, and it will just spit out words that have never been written before, so they aren't plagiarized, and it will be coherent. It will be an essay about a topic. Isn't that cool? Just a bunch of virtual neurons passing electrical signals, virtual electrical signals, which are numbers with decimals in them, to each other, eventually produces text. That is just glorious, in my opinion. That's so cool that we can do that these days. Have we seen this before? Maybe we've heard this fancy acronym. This is so insane, right? So, yeah, just to prove that it's cool, I have 2 pieces of websites that we could go to. I think if the first one doesn't work, then we'll go to the second one. This one's easier to type if it works. Yeah. So please go to this website. It's 6b dot, however you pronounce that, Eleuther? I don't know. ELEUTHER.ai. So please go here. I'll give you a few seconds to write it down. Sorry. That's as big as I can make it. Please go there, and this is essentially a smaller version of that GPT-3 neural network that writes text for you. They don't give away the full one for free, but somebody made a free version of that same kind of thing, just fewer neurons, I guess. And it will generate text for us. So it's called the GPT J6B. It's similar, but not as cool, not as many neurons. But you can give it like a sentence as a prompt, and then it will start generating things like I love computer science! Exclamation point. You can manipulate these random things if you'd like to. Top P, temperature, whatever those mean. That just inputs to the model. And oh no, unable to connect. Does that mean? It means probably there's not enough computational power right now for this website. So that's why I picked two. I'm sorry that this one's so long. Let me see if this one works, and then I will run the model. Yeah, it must be down right now, sadly. Maybe some of you got it to work. But let's try this one. Text generation API. I love computer science. Yay. So, and then it's just going to write stuff for you. I love computer science. We are in Silicon Valley now. It's in tech. It's the latest innovation that brings everything that's new and exciting to computer industry to life. The company will take over after Cisco has announced it, will not enter into an agreement with Microsoft to acquire its own cloud operating system. So all this is made up. It's not perfectly legible because it's not the full thing, but it's still pretty cool and pretty accurate. You can give it a piece of text. And so let me somehow share this link with you. Probably the easiest place to share this with you is that written nice page on our class website. We can all get there. So let me just paste this link here in group 0. Come on. There you go. So here's this other one that apparently works today. deepai.org/machine learning model/text generator. So that's where I put it. And you can just type some text, click generate, and it will start writing after that sentence. That's its prompt. And if you click it again, it's all random, so it'll probably write something different. So yeah, give it a sentence as a prompt, play around with that for a couple minutes, and share with your group members like cool sentences that it came up with. So take a while to play around with the latest and greatest in artificial technology, intelligence technology. And then we'll switch gears. Depending on the prompt, it could be pretty convincing. You can use that to write your essays now. All right. So yeah, hopefully that was fun, just playing around with that. It really could write anything, so like pick some random prompt. After I graduate, I want to blank. And I'll just write a random idea based on that. Let's see what the text generation API wants to do after it graduates. I want to earn. Interesting. I want to be a writer, so I want to be a musician. I need these kind of things before I go. Oh no, poor artificial intelligence thinks it's going to go. So yeah, it just starts rolling with whatever you give it, and I think you can imagine that the paid version of this, the cool GPT-3 one, it wrote this. Like, it's a bit more accurate. It's a bit more convincing. Okay? So I hope you found that fun. Let's keep on trucking, though. Got a few more things to do today. So the last thing that I want to talk about, kind of in addition to Turing test, once the computer passes a Turing test, it's like as smart as a human in theory, right? Maybe one day a computer will pass a human in terms of just sheer intellectual ability. It's very good at doing mindless stuff very quickly. That's what a computer is very good at right now, but maybe it'll be better at just general knowledge and general thought than compared to a human one day. And so that brings us to a topic called the singularity. Okay, so just like those chess and Go algorithms, AIs can start getting better than humans by training themselves, by playing against themselves. Essentially, computers could do that with each other, right? For just general human knowledge. They are thinking on their own right then, right? What if they could do the same? What if they could talk to each other and go to Wikipedia and study all of the Canvas pages for all the classes that exist in the universe and just keep learning? What if the same could happen for just general machine intelligence? Computers could teach each other and start getting better and better and smarter and smarter. That would eventually make it so that a computer is essentially like a human. It would function, think like a human, and eventually get smarter than a human, all right? So here's the idea. Here's the thought experiment with the singularity. Pretend that we make just one computer that's smarter than any human, right? The first computer that has more general intelligence than a human. Once that happens, we have created potentially a huge spiral, because we could just copy that very smart computer that's smarter than us and have a ton of smarter than human computers, right? And they could all be smarter than us, think better than us, invent cooler things. And then we ask those computers that are smarter than us to come up with a design for a computer that's even better than them, right? Because maybe they'll figure out how, because they're smarter than us. We built it. It was smarter than us, so they could build something smarter than them, potentially. So we ask it to invent something better, ask it to improve itself. A computer probably would never have been able, or a human probably would have never been able to come up with that design because they're just not as cool as those smarter than us computers. And we go off, we use those, like they give us the schematics, the smart computers give us the schematics for the even smarter computer. We build it and then ask it to build a better version of itself. And just keep doing that forever and ever, and we get super intelligence, right? That's called the singularity. That's when computers get so smart they can keep making themselves smarter and smarter and smarter, and just everything that we could ever hope for, we can ask a computer to do, and all of our dreams will come true. That's essentially the singularity. We have ultra-intelligent machines, smarter than any human could ever potentially be. Okay? And so a fun quote that goes along with that line is that the first machine that's smarter than us, the first ultra-intelligent machine, is the last invention that man need ever make, right? Because then we could start asking it to do the complicated stuff for us, to rule the world, right? Provided that the machine is docile enough to tell us how to keep it under control. Otherwise, it would probably take over, and there are plenty of movies based on that, right? So that is the singularity. We just need to make one computer that's smarter than us, and then it can make a better version of itself. And then that one can make a better version of itself. And we get super intelligence. That is the singularity. How cool is that? That's a fun little thought experiment. Maybe one day it would come true after we've passed the Turing test, after we've made a computer that's just as smart as a human. Any questions, comments about that? It's a little scary, I guess, but it is a possibility. All right, the next topic is completely different. I want to talk about logic stuff again. So I want to talk about qualifiers and quantifiers. Let's talk about how to logically think with these things involved. Okay? So let's first talk about qualifiers. Those are just words that you can add to normal English sentences, right? So here's a English sentence on the next slide. Qualifiers have to do with absoluteness, like trying to make sure that we don't say something that isn't true, right? Because nothing is ever absolute, especially when you're arguing something. There's always a special case that you got to watch out for. So you want to make sure that you're not just saying a bunch of sweeping generalizations, that's the term. Don't say a bunch of absolute things when they're not true, right? How can I make sure that my statements are correct, that they are not just sweeping generalizations? You would use a qualifier. So here is a sentence with a qualifier in it. Almost every day is unbearably hot in Fresno in the month of July, right? That is a pretty true sentence, in my opinion. But somebody could come along and say, no, there was that one day, just freak of nature, it was in the 80s. You remember that day? But no, my sentence is still correct because I said the word almost. Almost is a qualifier. If I said every day is unbearably hot, then this would be a correct counterargument. Like, no, you were wrong. There was one day that wasn't unbearably hot. But I said almost. That was a qualifier. Okay? And so here are a bunch of qualifiers that you use in your day-to-day speech, like none. This is never true. There exists an example of this. Almost none. Almost no days are cool in July. Some days are. Generally, it's hot. Almost always it's hot. It's always hot in Fresno in July. Those are just different flavors, right? Different qualifiers. They mean different things. Just there's a spectrum going on, right? So there's between none and all. There's a bunch of stuff in between. Those are qualified statements. If you use stuff in between. And that helps you be precise, right? I'm sure you can think of a bunch of examples of sentences with qualifiers in them that without them would be false, right? Probably the most relevant is a lot of people like to argue about is COVID vaccines, right? So COVID vaccines, for example, COVID vaccines are generally effective, would be a correct statement, right? Generally effective. I don't know the exact numbers, but like maybe 80% of the people who got the vaccination, something along those lines, they did not develop any bad symptoms, any extreme symptoms, or maybe 20% did, but they would have anyways if they got COVID. So 80% is not all, right? It's not all, unfortunately, but you could say stuff like mostly. Mostly this is true, right? Generally it's true. And the majority, and the vast majority. So those are some qualified statements. Does that make sense? You can't just say it's always the case that this thing is true, because sometimes it just isn't. There are definitely special exceptions, and nothing is absolute. Okay, so you have to qualify your statements if you want to be precise and make sure that you're not saying the wrong thing. This is the kind of sentence that we'd like to say. We'd like to be able to say this, something precise, something with a qualifier in it. We'd like to say that in logic. Give that idea to a computer and have it say, yes, true, no, false, right? So I guess the essence of a qualifier in a logic is called a quantifier. Okay, so I want to teach you a quantifier. Two different quantifiers. And these are part of logic. They're a way to qualify your logical statements, essentially. Okay, so we know our ands, our ors, our nots, all that stuff. But there's some more. There's some more that can understand these ideas, like all, sometimes. There are some logical operators for those. And so let's go do some math now. This is more math. Math time. Yay. So, yeah. This is the idea. This is what I'd like to be able to do. I'd like to translate qualified sentences into math so I can prove that that qualified sentence was true. Okay? That is my goal. So here are, let's see, how am I doing on time? Oh, I'm doing fine. Cool. So here are two quantifiers. These are the ones that I want to teach you. Okay? We can pretty much represent most of these qualifiers with just those two quantifiers. Here they are, plus like the ands, the ors, the nots, all the stuff that we know already. So in addition to these, we now have these, for all and there exists. So this symbol, when you see it, it reads for all. It means for all. And then this symbol, when you see it, you read it as there exists. So the way that they came up with these symbols is they took an A, they flipped it 180. They took an E, they flipped it 180. That's the idea. So yeah, when you see this, just read for all. When you see this, read there exists. And we can give precise meaning to these symbols, right? There are some other ones. There are some other symbols that talk about, that qualify like time. This thing is not true now, but it will be true an hour from now, something like that. And implicitly, that also means it's going to be able to talk about the future. These cannot talk about the future, essentially. But those are not as widely used. Okay, so I'm going to teach you these two. These will be important, especially if you go on into like a math major or a computer science major. For all and there exists. You'll be seeing those a lot. Okay, so here are some examples of both of these quantifiers. Here's the first one. Let's do an example of for all. All right, you can represent this question or this idea. Like, I would like to know all the numbers for which this statement is true, right? Every value of x, or I'd like to, yeah, for all, I'd like to know all of the x's for which this statement is true. Every value of x is greater than 5, right? I'd like to express that I have an x, and everything that it could possibly be is bigger than 5. So you'd write it like this. For all x, x is greater than 5. And this becomes a logical statement, right, that tells you what is true about your x. It's like I want to express the fact that whatever x could be, like maybe in my program I have a variable called x, it's always greater than 5. Okay? And so this will give you a true or false idea, right? Like we know if we assume that this statement is true, every value of x is greater than 5, for all x, x is greater than 5. If we assume that we know x must not be 2, x cannot be 2, right? Because this wouldn't be true for it. It's not greater than 5. 2 is not greater than 5. But x could be, for example, 7, right? I'm not saying exactly what x is, but for all values of it that it could possibly take on, maybe in my program, maybe somewhere else, just in life, that value is greater than 5. I'm representing a number that is greater than 5, essentially. Does that make sense? That is a true or false statement now. If you give me an example. Every value of x is greater than 5. That's something that I can represent now with this for all quantifier. For all x, x is greater than 5. Here's an example of there exists. I can use a there exists quantifier on a number. It's saying that, okay, something is true for at least one example, right? So there exists a number n that is both prime and even. This is a true statement, right? This is how you'd write it in math. Like there exists an n such that n is prime. We'll use like some English plus math. N is prime and n is even, right? That's how you can break it down into essentially logic is even, if you had a way to represent evenness and primeness as well. But this would be another statement. This is a logical statement now that could be true or false. And this is a true statement because what could n be to make this true? Do we have a value? Well, x can't be 7, right? Or sorry, n can't be 7 here. N can't be 7 in this example. That wouldn't make it true because, yeah, 7 is prime, but 7's not even. What is the one prime and even number? Boop, that one's x. We may be asleep today. It's 2, right? 2 is even and it's prime. It's the only even prime number. That's beautiful. So this is a true statement because there does exist an n such that n is prime and n is even. N could be 2. 2. Just pretend that n is 2. 2 is prime and 2 is even, so it's true. There is a number. There exists a number. I'm not telling you which one, but one of them is true for this. That's what this is expressing, okay? And we know that it's a true statement because n could be 2. Are there any questions about that? That's just it's a weird new idea, I think, and it will take some time to sink in, but hopefully you're getting the hang of it. There exists a number n that is both prime and even. Every value of x is greater than 5. For all x is greater than 5. There exists an n where n is prime and n is even at the same time. Okay? So, yeah. With that in mind, I would like you to, as a group, you don't have to write this down, try to specify, try to come up with, because this is what logic is really good for, to formally specify stuff, try to specify the property of sortedness in English, just in English, okay? We're eventually going to translate this to logic. What does it mean for a list of numbers to be sorted? And this is why we had to have the programming lecture on Monday, because here's a list, now you know what they are. This list is sorted. How would you explain to someone that's never heard the word sorted before that this list is sorted? What does that mean, right? Come up with an English definition that is as precise as possible for the word sortedness. Pretend that this person that you're talking to, like pretend I have amnesia. I don't know what the word sorted is. I never heard it before, okay? And then we'll translate our English idea to a quantifier-based approach using either for all or there exists or a combination of the two. But how would you define what it means to be sorted? That's going to give us good practice to use quantifiers with. Okay, so try as a group to specify what sortedness means. See if you can convince your partner that, your partners, that your definition makes sense, doesn't have any holes in it, etc. Give you a couple minutes to try that. How would you explain that list is sorted? L is sorted. All right, that's my timer. So, did anybody come up with a good definition that they feel like sharing? What does it mean that a list of numbers is sorted? How would you explain that to an alien or something? Yeah. Okay. Assuming that they're integers, how would you describe the arrangement? Okay, that's true. With respect to distance from 0, maybe? Something like that? That could work. Yeah, I like that. And so as you go further in the list, that distance would increase, potentially? Yeah. Something like that? Yeah, I like that. So that would work. It would get a little fuzzy if you talked about negatives. You'd have to use like absolute values and weird stuff like that, or just subtraction. But yeah, here's another idea. So essentially, a list of numbers is sorted because it's getting bigger, right? How would you got to break that down though, a little bit farther. Like, this is a graph of how the list is, but technically, right, this isn't always the answer. Like, 8, yeah, it's less than 27, 27 is less than 42, 42 is less than 79, 79 is less than 101. This is the kind of idea that means it's sorted, right? The next number is bigger. Does that make sense? Technically, you could also have a list like this, L prime. It's still sorted if it goes like 1, 2, 2, 2, 3, 3, 4, 5, right? So this is not taking into consideration everything, because there could be like a stair-stepping thing involved, like it stays 2 for a while, it stays 3 for a while, it stays 4 for a while, but it's still sorted, right? And so I think a better way to say it is every element, the next element, just look at every pair of elements right next to each other in this list. It's always the case that the left side is always less than or equal to the right side. That's what it means for a list to be sorted. Any questions about that? That's kind of how we would define it. In English, you'd say something like every element in the list is either getting bigger, it's bigger than its previous element, is getting bigger, or staying the same. It can stay the same as the last element for a while if it wants to. Staying the same. So that's probably how I would explain it to an alien, but there are equally valid ways to do it, especially if the alien knows advanced math. So, yeah, I think the best way to explain it is like this element is less than or equal to this element, and this element is less than or equal to this element. How could we talk about an arbitrary list? Like, I don't know what the list is, I just know it's sorted. How would you explain that to somebody? Because maybe the list had 1 million elements in it, but we know it's sorted. I think the right way to go about this would be to use indices, right? We know about indices in our lists now. This is index 0, this is index 1, this is 2, this is 3, this is 4. So it's always the case, you see, that 0, L of 0, is less than or equal to L of 1. And L of 1 is less than or equal to L of 2. Where these two numbers are off by 1, that's essentially what it's saying. Everything right next to each other, there's always this relationship. It's always less than or equal to. The next thing, the next index is greater than or equal to the previous index, kind of idea. Does that make sense? That's how we can define it. And then we can translate it to math, okay? And here's the math that you would figure out. Like, how do we say that L of 0 is less than or equal to L of 1, and L of 1 is less than or equal to L of 2, and so on and so forth for the entire list, regardless of how big it is? You would quantify over that index. You would say this. This is what it means for the list L to be sorted. For all the i's, for every index I that makes sense, that exists, for which this doesn't like throw an error or something, for every index I, L of I is less than or equal to L of I plus 1. And so for every I, it's talking about for every I all at once, for every I, L of I is less than or equal to L of I plus 1. Do you see how I'm writing that? Do you see how that makes sense? So translating the math back to English, it would be something like this. For every index I that makes sense for L, because maybe you don't want to go over it, go past the end, right? For every index I that works, L's element at that index is less than or equal to L's element at the next index. And so this is talking about every I at once. It's saying, ... You could set I to be 2, and it's saying, oh yeah, L of 2 is less than or equal to L of 3. It's working on every I all at once, L of 3. Okay, when I is 2, you get that. Maybe I should draw it a bit more like this. Let's see if I can. Yay, perfect. So when I is 2, this is essentially what it's saying. And when I is 3, it's saying that L of 3 is less than or equal to L of 4. Okay, and this works for every I. It's saying this for every I, and so all of them together at once, combined, if this is true, you're saying this kind of idea, and that proves, that's claiming, right? If it's true, it's claiming that the list is sorted. Does it make sense how this is quantifying over, we say, every possible index? It's talking about an infinite number of things at once. if the list is infinite sized. That's what for all gives you, a bunch of stuff at once. Are there any questions about that? So that's how we say a list of numbers is sorted. For every index I, L of I is less than or equal to L of I plus 1. So here's a quantifier. Here's our sortedness idea. Here are your other quantifiers. You have for all, you have there exists. Try to do this last one, then I'll do it for you. So here are your options, right? You have for all, you have there exists. Here's an example of what we did last time. But try to create a statement with quantifiers that represents the idea. Maybe go to English first, like we were doing on the last slide. Try to represent the idea that every non-empty list of numbers has a minimum, right? That is a true statement. Every non-empty list of numbers has a minimum. And so you'd have to specify what it means to be a minimum, all that kind of stuff. So you have to specify that this is true when the list is non-empty, so this one doesn't count, but this one has a minimum, this list has a minimum, there's the one in it. You could always find a minimum in a non-empty list. So here are 2 hints for you. Do we see where quantifiers could pop up? Every non-empty list of numbers has a minimum. Every looks a whole lot like one that we know, and has a looks a whole lot like one that we know. I think that should help. Okay, so with that in mind, try to come up with an English statement that looks a bit more like logic, starting from this, and see if you can introduce some quantifiers. Get as close to math as you can, as close to this kind of idea as you can, and then we'll do it together. Okay, but I want to give you some time to struggle before we do it, so that you can learn on your own. That is how learning happens. So see if you can represent that statement in math, potentially using indices. Every non-empty list, call it L, of numbers has a minimum. What's true when a number is a minimum? Also, what does that mean in terms of the entire list? What's true about the minimum? Why is it a minimum? All right, now that I've got you thinking, maybe it took you the whole time to think of what it means to be a minimum even. That's okay. I would like to walk you through this step by step. It's definitely a harder question. Okay, I would not dream of asking you this on a test, but I want you to try it. So what does it mean that every non-empty list of numbers has a minimum? All right, so we need to first be able to, like we did here, represent either an index or a list. Every non-empty list of numbers has a minimum. So we have to be able to reference the list in question, right? We have to give it a name. So the first thing we must do is we have to introduce a variable for that list, for some arbitrary list of numbers. Every non-empty list of numbers has a minimum. Let's call that list L so that we can talk about it for the rest of our mathematical statement, okay? And so here is the next step. This is the next, we start with this quote, and then we translate it to this kind of language, right? It's still English, but it's a bit closer to math, right? We notice that this looks a whole lot like for all, and has a looks a whole lot like there exists, I hope. So with that in mind, let's see if we can go further than this. So this is equivalent to the first bit, but it's a bit more mathy, right? So for all lists L, every non-empty list of numbers has a minimum, so we have to make sure that we have our side condition that L isn't empty. So if L isn't empty, then there exists a minimum value in L. So do we see where the quantifiers are plopping up? I'm explicitly said them now. So for all lists L, that's where that one is. Then there exists a minimum value. And also, I've introduced some logic stuff. Do you remember our if-then statements in logic? Those were implications. So it's all plopping up. We need them all to create this statement. Every non-empty list of numbers has a minimum. So this is the next closest thing to math. For all lists L, if L isn't empty, then we know it's not empty, right? Then there exists a minimum value. And now our job is to worry about what minimum means. Okay? So what does it mean for there to be a minimum, you might ask? Again, we have to mathematically specify that fact. What does it mean for there to be a minimum? We need to describe, right? We have to say what that minimum is with math. So what does it mean for a number to be a minimum value among a bunch of other numbers, right? I'm sure you've thought about this, but it's a very philosophical question, right? What does it mean when a number is the minimum? Well, that just means that it's the smallest, right? Comparing that with everybody else in the list, if you take the minimum value and you compare it with every other number in the list, it's always less than or equal to, right? That's what it means to be the minimum. Does that make sense? Are there any questions about that? Because that's going to be the key. Every other number in the list, it better be smaller than it. And there's the word every is plopping up again, so we need another quantifier, another for all inside of this definition of minimum. Hoo-hoo. So this is getting fancy. So we need to worry about every other number in the list, that this one's smaller. And so to talk about other elements in the list, again, we're going to need to talk about indices. So we have to quantify over every other element in the list's index. So we'll need even more variables to talk about those. We need a variable for the minimums index. We need the indices of all the other numbers. And so here is how you could do this. Here's how you could translate it. And I'll write it in math down here. Here's the correct answer, or a correct answer. There are multiple. So you take this as your starting point. So for all lists L, so for all L, if L isn't empty, then this whole thing is true. So the if is a part, and then you use the arrow to mean implication, and then the then part goes after the arrow. Remember that? So for all lists L, if L isn't empty, so L is not equal to the empty list, or the length of L, we can use Python, length of L, if that's greater than 0, then, so that's the if side, then the then side is over here, then there exists a minimum value in L. So there exists a minimum value, and we can talk about the minimum using an index. So there exists a minimum index, I'll call it min IDX, such that this index holds the smallest value among everybody else in the list. So this minimum index for every other element in the list, so we're going to have a for all, it's the smallest, it's smaller. There exists a minimum index such that for every index I, L of the minimum index is less than or equal to L of I. That is how you say that there is a minimum value in L. There exists some index of the minimum, such that for every other index, including itself, it's always less than or equal to. For itself, it will be equal to, right? Are there any questions about that? That was a bit complicated. So, trying to go back to English again. This is how you could explain it. You would say this statement in English, you'd read it like this. For all lists L, if L's length is greater than 0, then there is some index in L, we'll call that min index, that's what I'm doing here, such that for every index I in L, for every index including itself, it's always smaller. L at that index, at that minimum index, is always less than or equal to L of I. I don't say how to find the minimum. I just say that there is a minimum. There exists. It's somewhere. Okay? Are there any questions about that? So this is a true statement. We could prove it if we had enough knowledge about how to prove these things. But that is the full answer. That is how you represent precisely in math that every non-empty list of numbers has a minimum. Okay? Any questions about that? This is very fun for me. It might be very confusing for you, but I promise that with enough examples, you'll get it. For all lists L, if the length is greater than 0, then there exists a minimum index such that for every index, the L's value at that minimum index is less than or equal to that other index. Pretty cool. All right, so with that, let's go. I wonder if this one works now. Run the model. Hey, it works now. Let's try this one. That's exciting. May take up to a minute to generate. All right, let me talk about your assignment, then we'll go back. Oh, I finished. Cool. I love computer science. I would love to be a programmer someday and work in the field. There are many aspects of computer science that I enjoy and excel in. This is a much better model. This sounds like English, like complete human writing. The problem is computer science is such a broad field that it's hard to know where to start. If I could become a programmer, what would I do? I'd like to start by learning how to become a developer. Like this could totally write your essays, right? That's so cool. So yeah, try that website now that it's working. But what I'd like to do is release your next programming assignment. This will be due week 14, so you got a while. It's only week 11. But starting now, let's make sure that's a correct date. November 10th, if we are in week 11, so it's 1, 2, 3, 11, 12, 13, 14. Yeah, that's November 10th. Cool. I did it right. All right, so this one is very similar to the last program that I wrote for us, drawing a bunch of random squares with random colors and all that. So this one, your assignment is to draw a bunch of random squares and random triangles, okay? So it's your job to draw both, a picture that includes both squares and triangles that are all random, all right? So here's what you'll do. Here's the program that I'd like you to write. You're going to ask the user to enter some number. You can call that n in your program or something else as long as you keep track of it. And you're going to end up drawing n shapes. All right, they're going to be random. It's going to each time pick, oh, I'm going to randomly draw a square now, or I'm randomly going to draw a triangle now. So maybe it draws like 10 squares. If n is 50, it draws 10 squares and 40 triangles. Or if you give n a 50 again, maybe it draws 25 exactly squares, 25 exactly triangles, but it's going to be random. And so it's going to be different every time. But the user enters n, and that's how many shapes they want drawn. Okay? And then for n times, in a while loop, you count. Here's what you do. Set the color, the fill color, to be a random color, just like I did. There are even more colors than I talked about. There's a giant list of weird, cool colors. Here they all are. Python knows about all of them. You can include that entire set if you'd like. So you got to set the color. And then you need to randomly pick each time, am I going to draw a square right now, or am I going to draw a triangle right now? It could be either one. It should be random. It's like a coin flip. Okay? So when your program runs, it should draw some squares and some triangles. The total shapes will be n. It's going to be different each time, though. Okay? And then you randomly pick the size and location again. Okay? And then you draw it at that randomly chosen location. Either it was a square or it was a triangle. So n shapes total, but it's random each time. So maybe if these are types 10, it will draw 4 squares and 6 triangles. And if these are types 10 again, maybe it'll then draw 7 triangles and 3 squares, as long as it adds up to 10. It'll be random each time. Okay? You randomly pick whether to draw a square or a triangle each time. I hope that makes enough sense. So n shapes total, no matter what the user types. Any questions about that? So you're going to use a lot of my code. I think I hard-coded 50 or something. You're just going to use the n variable that you get from the user. And you already know how to draw triangles randomly. That's part of your previous assignment. And so you'll add on to that, right? Now you're going to draw squares or triangles randomly. And you'll also introduce new colors. So please follow all these instructions. Make sure you get full credit. But that is your assignment. Are we good with that? So randomly draw squares and triangles this time. As many as the user wants you to draw. And I think that is all. Yeah, that's everything that I wanted to talk about today. So the rest of the time is yours to work.